A modern AI compute cluster creates a heat density that pushes hardware to its physical limits. Keeping GPUs operational requires immediate, flawless chilled air delivery. Inside the servers, IT teams track processor utilization, memory bandwidth, and core temperatures down to the millisecond. But the physical systems outside the server chassis are often entirely disconnected from that data loop. High-density machine learning workloads run constantly at maximum capacity. This concentrates extreme demands into facilities that must maintain absolute, uninterrupted thermodynamic stability to avoid throttling the compute. Most traditional building management systems, or BMS, provide a reliable view of the core data hall. They map the main aisles and track ambient room conditions, but their visibility usually stops at the walls of the server room. This creates a telemetry blind spot. The facility relies on a network of peripheral assets: remote pumps, external water tanks, backup diesel supplies, and underground pipelines. Because they are difficult and expensive to wire, they are often left unmonitored. Infrastructure problems begin as small deviations in these dark zones: a pressure reading dropping in a distant mechanical room, or differential pressure slowly rising across a strainer. Without telemetry, that deviation goes unnoticed until it cascades backward through the cooling loop, starves the server rack of its thermal delivery, and triggers a critical high-temperature alarm at the GPU. AI compute uptime requires continuous remote monitoring across 5 distinct domains of physical infrastructure. If any one of those layers degrades, the digital hardware is exposed. We can eliminate these blind spots without ripping up concrete or trenching new copper wire. Engineers can retrofit wireless sensors directly onto existing assets. This is powered by low-power wide area networks, or LPWAN. Compute availability is now bound to the thermodynamic and fluid dynamic performance of the facility itself. We start mapping this physical architecture at Layer 1, the data hall and airflow. High-density cooling is about precise flow vectors. Cold air must be forced into specific intakes, and hot air must be extracted through specific exhausts. Measuring the ambient room temperature tells an alterator nothing about how well that air is moving. To verify that cooling is actually being delivered, operators measure differential pressure across the delivery mechanisms. This chart shows the pressure difference across an air handling unit filter. As dust accumulates over time, the resistance rises and the pressure drops on the exit side. This metric provides an early, mathematical warning of airflow restriction. Inside the server cabinets themselves, facilities maintain a slight positive pressure. This ensures that conditioned air flows strictly outward, creating a thermal barrier that prevents external contaminants and hot exhaust from leaking back in. A sudden drop in that pressure profile instantly flags a containment breach. A technician leaves an aisle door open or a ventilation fan degrades, and the thermal delivery is compromised. Capturing these micro fluctuations requires ultra-low-range air pressure sensors, deployed exactly where the air enters and exits the controlled zones. By tracking pressure differentials instead of relying solely on thermostats, operators prove that the required volume of cooling is reaching the hardware before the equipment heats up. Moving outward from the data hall, the architecture extends into the mechanical rooms. Layer 2 is the cooling infrastructure. This is the network of chilled water lines and direct-to-chip liquid cooling loops that absorb and transport the heat away from the servers. Look at the pressure readings across this heat exchanger. Comparing the input pressure to the output pressure is the most reliable way to diagnose internal scaling, fouling, or blockages deep inside the plumbing. Measuring the suction and discharge pressure directly at the pumps reveals hydraulic instability. Erratic fluctuations indicate trapped air or a degrading impeller that will soon fail under load. These loops carry expensive fluids through sensitive metallic infrastructure. Measuring conductivity, pH, and turbidity ensures the chemical treatment is working and prevents severe internal corrosion. The cooling loops connect outward to Layer 3, water and sustainability. Dissipating the thermal load of an AI campus requires hundreds of thousands of gallons of water circulating between the internal mechanical plant and the external cooling towers. By attaching digital interfaces to the facility's existing makeup water meters, operators extract live consumption data. This feeds directly into the Water Usage Effectiveness, or WUE metric, keeping the site compliant with strict sustainability targets. If an automated makeup valve fails, a cooling tower basin can quietly lose its water inventory. Evaporation continues, but the supply is gone. Continuous level sensors installed over the basins and storage tanks track the exact volume of water available, preventing catastrophic dry running of the pumps. An AI compute cluster is entirely dependent on the thermodynamics of its water loops. Controlling that heat requires complete visibility over fluid dynamics and water inventory. Pushing to the absolute perimeter of the facility, we reach Layer 4, power resilience. The data center relies on heavy-duty backup generators to survive a grid curtailment. Those generators are useless if the local fuel inventory is compromised. Sending technicians out to perform manual dip checks on diesel tanks across a sprawling campus introduces human error, high labor costs, and dangerous uncertainty between readings. This chart overlays continuous level sensor data onto the tanks. It maps fuel depletion trends in real time, calculating exactly how many hours of compute time remain, so operators can orchestrate safe refueling logistics. The final physical domain is Layer 5, site and utility infrastructure. Data centers depend heavily on buried municipal pipelines. Monitoring the remote pressure-reducing valve chambers at the edge of the property catches fluctuating supply pressures before they destabilize the facility's internal pumps. During severe weather, unmonitored stormwater networks can back up. Submersible level sensors in the drainage channels alert facility managers to rising water levels before the site floods. These unwired perimeter assets exist entirely outside traditional control systems. Without dedicated monitoring, they remain the most dangerous blind spots on the campus. Extracting this data presents an architectural problem. Running physical copper wire to a remote diesel tank, an underground pipe, and an external cooling tower is prohibitively expensive. We solve this using LPWAN, low-power wide-area networks. Battery-operated sensors transmit data over long distances, forming a wireless telemetry backbone across all 5 layers. For a single contained campus, operators deploy LoRaWAN. This creates a dense, private, facility-controlled network that penetrates thick concrete and spans the entire property without relying on external cell towers. For geographically dispersed utility assets or remote edge AI sites, cellular protocols like narrowband IoT transmit the telemetry directly to the cloud. When retrofitting an existing facility, operators do not want to tear out perfectly functional analog pressure gauges, water meters, and existing instruments. Instead, they use sensor interfaces. These small transmission nodes wire directly into the legacy hardware. The interfaces instantly digitize standard 4 to 20 milliamp signals, legacy Modbus data, and mechanical pulse outputs, bringing decades-old equipment onto the wireless network. With LPWAN and these sensor interfaces, engineering teams can overlay a modern, continuous monitoring grid onto an existing footprint in days. Field telemetry generates value when it reaches the control room. This data aggregates into a unified view of the facility's entire physical health. An isolated pressure reading is useful, but the true operational advantage comes from analyzing long-term behavioral trends across the assets. The traditional facility model is reactive. Wait for a red alarm to trigger, then scramble technicians to troubleshoot a failed system. Continuous monitoring enables condition-based intervention. This chart tracks differential pressure across an air filter. The trend line reveals the degradation rate over a 30-day period, crossing into a yellow warning zone weeks before failure. Crossing these thresholds automates workflows, allowing managers to schedule replacements during planned maintenance windows. A holistic architecture allows teams to correlate variables, like tracking a fuel inventory dip across a global portfolio in real time. The actual uptime of a high-density cluster is a product of heat rejection, fluid dynamics, and power stability. By bridging the telemetry gap across the data hall, the cooling loops, the water inventory, the power reserves, and the site utilities, operators secure the physical foundation required to guarantee AI compute results.